So our next speaker is Yihong Du from University of New England, Australia, and he will speak about spreading profile and nonlinear Stefan problems.
Thank you. Also, I want to thank the organizers for the kind of invitation. So the problem I want to consider is this one. So this is a typical kind of a semi-linear parabolic equation, and with initial condition. And what's unusual is that this equation is satisfied for x in a varying domain. So omega changes with t. And on the boundary of omega, which we denote by gamma of t, and we assume that the solution takes value 0. So it's a 0 boundary condition. But to describe the evolution of the boundary, which we call a free boundary, and we use this equation. So this is a kind of a typical semi-linear problem on the changing domain with the Dirichlet boundary condition, and this equation governs the evolution of the free boundary. And this actually is the usual one-phase Stefan boundary condition. And so U0 is given, and we assume that U0 is it's a positive inside omega 0. Omega 0 is the initial region of omega. When t equals 0, omega t equals omega 0. And this mu we assume is a given positive constant. And for this f of u, we assume that it's one of these three kind of standard nonlinear functions. I'll explain in a moment a bit more about what is monostable, what is bistable, what is combustion. So to say, using a graph to describe these, so a monostable is 1, so it's a positive between 0 and 1, and a negative after 1. So 0 and 1 are zeros of f. So it's called a monostable because if you consider the corresponding ODE problem, and 0 and 1 are stationary solutions, 0 is unstable, 1 is stable, so it's a monostable. And this is called a bistable because 0 and 1 are both stable stationary solutions of the ODE problem. And now in this case, we have a middle 0. And f is of a combustion type if it's identity 0 between 0 and some positive number theta between 0 and 1, and then positive and then negative. And these kind of nonlinearities are considered is because in spreading problem, these are three important and typical kind of nonlinearities. Now the physical meaning of these free boundary condition. So if we look back, I'll write this here. So this free boundary condition, and at the free boundary require you to satisfy that. So this really physically means, so at any point on the free boundary, and so the evolution of the free boundary is moving in the following fashion. So it moves in the direction of the orthonormal and with this velocity. And this square just appears because of this kind of manipulation with the equation. So if we consider the simpler spherically symmetric setting, and then the free boundary would be a sphere, and with a changing radius, and then this free boundary condition would reduce to that one. So the derivative of the radius equals this. And we know that this problem always has a unique weak solution. And it's, well, I won't define what we call a weak solution. It's a bit complicated. But in any case, in such a situation, and the omega t is just where the solution is positive for fixed t, and that's the free boundary is just understood as the boundary of this positive set of U. So if f of u is identically 0, then we are back to the classical problem, and which was studied because it describes the melting of ice in contact with the water. And in such a situation, U represents the temperature of water, and the free boundary would be just the interface between water and ice. And if you think in that direction, you could get a nonlinear Stefan problem if you replace water by some chemically reactive and heat diffusive liquid. And in such a case, f of u would represent the reaction. But this kind of a problem has not attracted much attention. And we were interested in such a problem because we were thinking about a different situation, and we consider spreading of some biological or chemical species. And in such a situation, U represents the density of the species under investigation, and the free boundary would stand for the spreading front. So you have a species concentrating on omega t. Outside of omega t, there's no such a species. And then the boundary of omega t would be just the front of the spreading species. So if you consider it in such a situation, and then you can derive this free boundary condition by using this assumption. So you, basically you assume there's a loss of population at the front. There's a sacrifice, and then you would derive the free boundary condition. And the constant mu in this condition would be just 1 over this k. Well, for such a situation, actually the spreading problem has been classically investigated through this Cauchy problem. So the same kind of f of u, and you can consider the same kind of initial function, but you don't put any restrictions on x. So x varies freely on Rn. And in such a case, and you investigate how the solution evolves, and that can help you to understand the spreading situation. I'll recall some result for the Cauchy problem in a moment. But now I just want to ask the question. So if we have this classical Cauchy problem to represent the spreading of a species, and then we propose this new free boundary problem. So the same kind of equation, the only difference is that, so now x varies on a moving domain, changing domain. And we impose free boundary Dirichlet boundary condition, and we have this free boundary condition governing the spreading, the evolution of the free boundary. So this is problem 1, and the Cauchy problem we call problem 2. But for the Cauchy problem, there's lots of result, and we know quite well in many situations. Now we want to say, well, are there differences between 1 and 2, and are there similarities? So now let's first recall the basic features of the Cauchy problem. And in the Cauchy problem, of course, by the maximum principle, remember we always assume that f at 0 is 0. for all three kinds of nonlinearities, they share this common property. So now, because of the maximum principle, and if you consider the Cauchy problem, we use capital U to denote the solution, and then the solution is a positive everywhere as long as t is positive. But if you consider a spreading problem, you intuitively think that the population concentrate only on a finite part of the domain. Then how do you use this Cauchy problem? Well, this is not a big problem, so you can assume, you can choose a small positive constant delta such that you regard this region as where you can observe the population. If the population density is below delta, you just assume that there's no population. So this would be the populated region, omega delta of t. And when spreading happens, that is, you have a new species, and it can establish itself, and then that's the situation in mathematics. We say when t goes to infinity, the solution goes to 1, because we normalize that f1 is 0. And in such a situation, there's a well-known result saying that, well, if you consider the boundary of this set, which is this gamma delta of t, and it's squeezed between two moving spheres. The sphere's radius increases with the t, but kind of linearly. And this constant c0, so epsilon can be as small as you want, but this c0 is a fixed constant. It is usually called the spreading speed. And that can be determined by this traveling wave problem. So the same kind of f, but here both c and q are unknowns. So you require these conditions at the boundary of R1, and you normalize it so that at 0 is half. And this C0 is uniquely determined by this problem. Of course, depending on whether F is a monostable or bistable or combustion case, and so this C0 changes. And furthermore, so in the monostable case, C0 is the minimal value such that you have a unique solution. So actually, for any C greater than or equal to C0, if F is monostable, you have a unique solution. But for the bistable and combustion case, U0 is the unique value for this problem to have a positive solution, to have a solution. In any case, U0 is uniquely determined. And if your initial function for this Cauchy problem of this equation is really symmetric, and then you can get much better result than this rough description for the spreading. Well, now what's the basic feature of the nonlinear Stefan problem? Problem 2. And you, in a recent joint work with Hiroshi Matano and Clay Wang, and we proved that. So we have these 5 basic properties. Firstly, omega t is expanding with time. And secondly, we have regularity for the free boundary. That's usually it's a very difficult problem, but we were able to get the regularity. It's like if I so if this is omega 0, so that's the initial omega 0. And our result says that, well, outside the convex hull of omega 0. So basically, the convex hull would be, in such a situation, would be this one. And we can imagine at some time, at some t positive, and you might have the free boundary evolving that way. And you might have a particular time so such that these narrow bits touch each other. And then after that time, so they separate. So if omega 0 is what I draw, and then you cannot guarantee smoothness of the free boundary all the time. And singularity can happen, even if omega 0 has a very smooth boundary. But in any case, and so the part outside of the convex half of omega 0 is always smooth. And then because it's increasing in t, omega t is increasing in t, we can talk about the limit as t goes to infinity. And we can show that this limit is either the entire space or it is a bounded set. It cannot be, for example, a half space. When omega infinity is bounded, we can show, so your solution u has to go to 0. And in the language of population problems, that says that the population vanishes. And if omega infinity, the limit, is the entire Rn, we can show that for all large time, the free boundary is always smooth. And it is a smooth closed Hopper surface. And furthermore, this is squeezed by two spheres of a radius m of t, and this is m of t minus a finite constant. And of course, in such a situation, mt goes to infinity as t goes to infinity. So that basically says that, so when t is very big, if the limit of omega t is entire Rn, so these small bits will shrink to a point or shrink to a lower dimensional manifold and then disappear. And we only have this outer bit, and it's getting rounder and rounder. So if you normalize it to unit volume, for example, the free boundary would be converted to the unit sphere. And then we can also show that this mt that goes to infinity like a linear function of t. And this constant C0 star is, for the free boundary problem, is also a spreading speed. And these can also be determined by a kind of a traveling wave problem. So we call it a semi-wave because of the difference. So this Q, so if we compare this ODE with the earlier one, so the same equation, the only difference is that this is in R1. Now here is in the positive half of R1. And at 0 is 0, at infinity is 1. But this time, for all three types of nonlinearities, we can show we only have, if we look for the pair, C and Q are both unknowns, we only have a unique C0 star. So even for monostable case. And that is, so this problem has a unique solution pair, C equals C0 star, Q equals, well, Q C0 star. And of course, we require these Q satisfy this extra condition, and this arises because of the free boundary condition. So this mu is from here. So if I use these to describe the usual traveling wave, so the profile is determined by capital Q, and its speed is C0. And now I have this semi-wave, and it reaches 0 at a finite place, and it moves at a constant C0 star. So now we can see some similarities. So the fronts of both the Cauchy problem 2 and the free boundary problem 1 can be approximated by spheres. And the approximating spheres, so that's when spreading happens. And these spheres go to infinity at some constant asymptotic speed. So C0 and C0 star, respectively. And these two are usually different. And they have a relationship. So these C0 star, of course, depend on the mu in the free boundary condition. And it's increasing with the mu, and when mu goes to infinity, the limit is C0. So this C0 star is always less than C0. But as mu goes to infinity, the limit is C0. And actually, we could show actually the entire problem, the Cauchy problem, may be regarded as the limiting problem of the free boundary problem when this mu goes to infinity. So you look at a solution, the weaker solution of 1, to denote this by u of mu, and the varying domain is denoted by omega of mu, and then we have this relationship, if you choose the same initial function. So we maybe call the Cauchy problem a limiting problem of the free boundary problem. Now let's look at the differences. The first difference arises when we look at whether spreading happens. So if we consider the classical Fisher-KPP nonlinearity, that's a kind of a monostable nonlinearity. And for the Cauchy problem, there's a well-known hair trigger phenomenon. So as long as U0, the initial function, is not identical to 0, the solution, capital U, would go to 1. So spreading always happens. But for the Stefan problem, we have a spreading vanishing dichotomy. So if you use this mu as a parameter, we can show that we have a critical mu star, such that vanishing happens when mu is less than or equal to mu star, and spreading happens when mu is greater than mu star. And then next, we want to show that even if spreading happens, so both for the Cauchy problem and for the free boundary problem, spreading happens, and that their spreading behavior, if we look at their fine behavior, we will also find big differences. So to do that comparison, so we look at these reduced symmetric situations. So because when spreading happens, our earlier theorem says that so the free boundary looks more and more like a sphere. So it's reasonable to look at these reduced symmetric cases. And in such a case, and we can show that so the free boundary now is described by the radius of the sphere. So free boundary is always a sphere because we are in the reduced symmetric case. So you just want to understand the movement of the change of the radius of the sphere. And these change like that, we can show. And also the solution behaves like the semi-wave. So these small q is the one I showed before, is this one. So it behaves like that, moving to infinity at this constant speed. But we should be careful here. So in dimension 1, this capital N is the dimension of space. In dimension 1, we don't have this log t term. But in high dimension, this appears. So there's a logarithmic shift. And this C1 star can be calculated using the C0 star and the Q, the semi-wave profile. Well, if now we look back to the Cauchy problem, the radial situation, and we also have a fine result on how this solution capital U. So now because U0, the initial function is reduced symmetric, by uniqueness, the solution is reduced symmetric. And this capital U can be approximated by this terminal wave profile capital Q in that way. So that is for the bistable and combustion case. So we also have this n-1 here before the log term. In particular, if n equals 1 in one space dimension, we don't have this shift, but in high dimension we have. But what's very different is that for the monostable case, including this Fisher-KPP case, Well, this is not capital N minus 1. This is n plus 2. You mean one space dimension, there's a logarithmic shift. So that's one big difference in behavior compared to the free boundary, the Stefan problem. So in the radial Stefan problem, so this profile is kind of synchronized. Of course, these C0 star, C1 star change when you change the nonlinearity, but the result is always in this uniform fashion. So there's no difference between monostable, bar-stable, and combustion in the form of this result. But for the Cauchy problem, there's a big difference. And I'll just comment very briefly. So for this theorem 3 and the n equals 1 case and the n greater than 1 case are actually treated in two different papers. And so for n equals 1, we could borrow the ideas in this classical paper of Pfaff and McLeod. But for this n greater than 1 case, and we have to rely on several new ideas. And the proof also is much more involved. That's a 22-page paper, but this one is 39 pages. I think I'll just skip this one. And so these are some other related research. I think I'll just stop here. Thank you.
Are there any questions?
Any result concerning stability of the profile if you change the reaction term F? For term F, if you
Yes.
change F,
Yep.
how do you perturb the...
Yes. So our F is
It's given, yeah. Fixed.
if you
Change it.
if you belong to the same class,
Yeah.
and everything changes
Yeah, but
in a
if you are
gradual
close
way.
to pass from one class to the next one.
Yeah, we didn't check. Yeah, that could be very difficult because that involves two kind of limits. So we let t go to infinity. That's for one thing. The other is we change f like we let a sequence of fn goes to f. Yeah, but yeah, that's an interesting problem.
Yeah, but you, the final result depends on an ODE analysis, so maybe you can do it.
Yeah. So, definitely for this C0, this traveling wave thing, and it should vary continuously with the f. Yeah, but for the
Could you please go back to the theorem 1?
Yeah.
Just my question.
Yeah.
Here you say that in item 2 the function should be sufficiently smooth. But
Yeah,
what
yeah.
about this alpha?
Yes, sorry. Yeah, alpha is between 0 and 1. Yeah.
Between 0 and 1.
Yeah.
And the same restriction on the next theorem, because in the next theorem the same.
No, actually, it's only for this regularity. We need f when it's close to, that's only near 0. And in a small neighborhood of 0 is a C1 alpha, because that affect, because at the free boundary, u equals 0. And away from 0, usually C1 is enough. And also for the other results, for all these other results, for radially symmetric case, C1 is enough. We don't need this extra smoothness, 0.
But in this case, alpha between 0 and 1.
In the general case, yes. For radially symmetric case, C1, FC1 is enough. We don't need F to be C1.
Okay, but please theorem 2. You
Yeah.
have also parameter and not clear.
Here, C1 is enough. Yeah. So the theorem 2 is basically we proved by ODE.
Okay, thank you.
I would like to remark
Yeah.
that in the one-dimensional case,
Yeah.
when f, your function f depends on the heat flux,
Yeah, yeah.
when a Dirichlet condition is imposed, I know some paper on this.
Oh, thank you. I want to know the details. Yeah, thank you.
So when mu equals mu star, the extinction behavior will be non-generic. So have you understood that case?
Mu equals mu star is the what behavior?
The time dependence of the extinction behavior
Yeah.
will be subtle, I think.
But we only, because we, for the for boundary problem, we only consider the initial function is positive on omega 0, and at the boundary is 0. It basically is like, if you consider the corresponding Cauchy problem, it's like we only consider these U0 with the compact support. If you allow U0 to be positive everywhere